This is cosine squared phi 0, 1, 0. This is my mass matrix, okay? Any question about that? So, and we move forward, we get our Lagrangian. This is just dynamics. T minus V, let's assume no gravity. So this guy is 0, so it's just T. And please go and do your equations of motion. Partial L, partial theta dot, yada yada, minus partial L, partial theta is 0, and the same for phi. You can see now it's, if mass is unity, this is the exact same thing that we worked with before, the same Lagrangian that we worked out. We got the same equation. I'm going to go and read them directly. They were something cosine squared and negative 2 cosine sine. So this is cosine squared, negative 2 cosine sine, theta dot phi dot, and this was phi double dot plus sine cosine theta dot square is 0. So we typically write them as a matrix cosine squared phi times theta double dot and phi double dot plus something equals 0. So this is 0, 0, 1, right? If I just read them, and here whatever left, cosine sine theta dot phi dot and sine cosine theta dot square. So typically in mechanics, this is again the mass matrix times q double dot plus some centripetal and Coriolis forces. Okay? Equal the forces on the right hand side. And you can see the equations are exactly the same. The equations are exactly the same. So if you start with nabla, just covariant derivative, did nabla gamma prime is 0 or qk double dot plus gamma I jk qi dot qj dot, you get a geodesic straight line from the derivative perspective. Or you start with a GE that is compatible with nabla, and you minimize the energy of the curve based on that G, you get exactly the same equations of motion. Or if you start with a unit mass rolling over your manifold, right? And just write down the equations of motion using whatever, Newton's equations of motion, mass times acceleration equal forces, Lagrange's equations of motion like we did here, or Hamilton's, whatever way you like to write down your equations of motion, they're going to be exactly the same. Okay? So all these are equivalent. Any question about that? I'm going to generalize it now and show you how this equivalence from a general perspective. But you saw it at least in the example. Any questions so far? Any question?
If we had any external forces, would the equations of motion still follow the geodesic?
No. Yeah. We can modify what do you mean by the geodesic too. So we'll have basically a new geodesic. Yeah. So here is the generalization, geometry of mechanics. Sometimes we call it geometrization of mechanics. So, I mean, the geometry is clear. We have our Q configuration coordinates live on a manifold by definition. So the Q dot, the velocities, they live on the tangent space of that manifold here, right? And the kinetic energy typically is written as, like I said, for any mechanical system, Q dot as a rho times the mass matrix times Q dot. So this is 1/2 Mij Q dot I Q dot J, with mass matrix by definition for a mechanical system is positive, definite, and symmetric. So again, by definition, when you look at this, I don't care where you come from. Look at this. This is a matrix that is positive definitely symmetric, defined on the entire manifold Q. So indeed, this is what? This is what? What is this thing? It's a Riemannian metric. It's a Riemannian metric on Q. So the kinetic energy is a Riemannian metric on the configuration manifold. Okay? It's a way to measure distance on the configuration manifold. Because it tells you a way of doing dot product between two vectors. If I forget the source that it's a kinetic energy, I don't care about it anymore, and I have here two vectors that are different, not q dot and q dot anymore. Two vectors, the result is a real number, and I can use that to measure distance on the manifold. So the kinetic energy is a Riemannian metric. That's okay, that's good. How we derive the equations of motion in mechanics? How we write the equations of motion? Well, there are several ways. Like I said, Newton's, Lagrange's, whatever, Hamilton. I will choose here the principle of least action, which we talked about a lot in 241. What does the principle of least action state? The trajectories are such that, what? Anybody remember? Trajectories are what? Anybody remembers?
The action integral is minimum.
Yeah, the action integral is stationary, well, let's say minimum for here. So the first variation of the action integral is 0. What's the action integral? Is t minus v, right? The integral of the Lagrangian. The first variation is 0, so it's as if I want to minimize this integral. And like I said, let's now forget this guy, the potential. We'll come back to it later in this lecture. So this is the integral of the kinetic energy is 0. So far, this has nothing to do with geometry, right? This is just calculus operations problem. Actually, it was just a principle. By Bourtui, right, when we discussed, he just came up with this principle. Like Newton's principle, what's that? The force is linearly proportional with the rate of change of linear momentum. Okay, it's a principle. We start with it. We start with this guy. So over there, here now, I have some geometry. I have a Riemannian manifold. I have a manifold called Q, and I have a Riemannian metric on it. It's called T, right? This is a Riemannian manifold. This is my M, the manifold. This is my G. And if you want to get the geodesic, how you get the geodesic? Well, I need to minimize the energy of the curve. So I need to minimize the first variation of the G, which is simply T is 0, right? This is what we studied today. Give me a manifold, the Riemannian metric on it. The geodesic is just the minimum, which is the first variation, the first derivative of this integral is 0. If makes you feel better, this is G of Q dot and Q dot, right? And you can see that these are indeed equivalent. They are exactly the same. The first variation of the integral of kinetic energy is 0. Here we arrive at it from this perspective. It's a geodesic on Q. Here it's just the principle of least action. This statement is beautiful because it includes geometry, mechanics, and calculus operation in one line. So here is the geometry. Your motion trajectories satisfy this equation, i.e. they satisfy this equation, actually the same equation, but it's just a different perspective. Satisfying this equation means they are geodesics. So the trajectories are geodesics. Geodesics of the kinetic energy Riemannian metric on In other words, your trajectories or a free particle, when you look at it from this perspective, a free particle moves along a straight line, correct? When you look at it from this perspective, well, it's nothing actually but Newton's first law. But Newton's was concerned with R3. Here we're just generalizing it. It's Newton's first law, right? A free particle moves in a straight line with a constant speed. This is the thing. But he was working in R3. Now we're working in whatever space. I don't care. Give me any space. It's still a straight line. Okay? Any question about that? This is very important, and like I said, it's quite beautiful correspondence between geometry and mechanics, because if you give me a mechanics problem like here, a bowling rule over the sphere, and you're asking me to find the equations of motion, I can completely ignore the dynamics of it if I like math and geometry and go and compute geodesics. I'll just ignore that it's a dynamics problem and I'll solve an exactly equivalent geometry problem. What's that? Well, your ball is rolling on that surface, I don't care about it, okay, it's some surface. I will go and compute the straight lines on that surface. These are your motion trajectories. The equations that govern the straight line here, they are your equations of motion, exactly the same. And vice versa. If you have a surface, if you are a geometry person, or you have a surface, and you want to compute the geodesics, it's a pure geometric object, the geodesics, straight line along that surface. I will completely ignore it. I'm a dynamics person, I love dynamics, so I'll go and imagine a mass, unit mass, a particle of unit mass, rolling over this guy, and go and apply Newton's equations of motion, force equal mass times acceleration. The resulting equations are the equations governing the geodesics. So it's complete equivalence between geometry and mechanics. If you are a physicist and want to find Christoffel symbols, which is, for them it's very hard to physics people, how to find Christoffel symbols. I will imagine a ball of unit mass rolling on this guy and write down my Newton's equations of motion. And the resulting equations, I will just make the equivalence between the Christoffel symbols and get the Christoffel symbols. Okay? So this is quite important. Any question about this equivalence?
Professor, if you have a non-conservative force, does this equivalence hold?
Non-conservative force. Let me think. No. But we can work around. If I have a non-conservative force, and if I can, because, well, like, if I can still write it in a Lagrangian perspective, like the Lorentz force. The Lorentz force is a non-conservative force, but I can still write down as in a Lagrangian framework. Then yes. So it depends on the type of the non-conservative force. So actually this was an instrumental tool in general relativity. I will spend the rest of the lecture talking about general relativity, or the way to general relativity, how it's evolved. Any questions so far? Any question about this equivalence, which I believe it's very important, between geometry and mechanics? So I think everything started from Michelson-Morley experiment. This is just 30 minutes on special relativity, general relativity kind of thing, just giving you an idea. It's a little bit more detailed than the version in 241. I'll give you how we can recover Newtonian mechanics from general relativity equations. So Michelson-Morley experiment, 1881, and then he repeated it 1887 with Morley, so first Michelson alone. What was the experiment? Here is the experiment, and I have a nice picture for it. So this is here, Wikipedia of course, Control V. What is that? Wow, this is super bad. Please, doing everything? No? Yes. Doesn't do undo. Okay, so delete. No. Wow. So that's okay. Anyway, so we can do the following. So here's the experiment. Anyway, I'll have to leave it there and continue afterwards. A light source, and this is partially silver-coated surface. So part of this beam will go through, and part of it will be reflected. Okay. So this guy moves in this direction, this guy moves in that direction. So they have 90 degrees between them. The point is, according to wave theory, the distance, the time it takes to cover a distance d, and your wave is moving with a velocity c, but your source is moving with a velocity v. What's the source? I mean, this is on Earth, and the Earth is moving with 100,000 kilometers per hour. So the Earth is naturally moving, your source is moving. It depends on how aligned, according to the wave theory, how aligned the velocity of the source and the velocity of the wave. So this is like v cosine theta plus something like, I don't know, c squared minus v squared sine theta squared. These details are not very important. But at any rate, because these two rays are moving with different thetas 90 degrees apart, the arrival time should be different, right? So, because the two rays are 90 degrees apart, so the arrival time depends on theta, obviously. So there's going to be some delta t expected. So Michelson did this experiment, and then repeated it 6 years later with Morley. Yet the same result, there is no considerable delta t, there is no delta t, which means that c is independent of the motion of the source. Okay? I have my own opinions, but I'm just telling you the history here. So this is Einstein. Special Relativity, 1905. He started with, the paper name is title is very expressive, electrodynamics of moving bodies. So there is dynamics, Newtonian mechanics here, which is the only thing known at the time, which is equivalent to Lagrangian. So Lagrangian is not more, just an easier way of writing down the equations of motion, but the same meat.